A central tension in applied machine learning is the trade-off between accuracy and interpretability. This is a challenge that's basically haunting almost every major industry right now. I mean, think about it. Do you want an AI that's incredibly accurate but operates as a total black box? Or do you want a model you can actually understand, but you have to sacrifice raw predictive power to get it? In high-stakes fields like big tech and quantitative finance, this isn't just some academic thought experiment. It is a literal multi-billion-dollar dilemma.
Hello and welcome. I am thrilled to be your host for this explainer today because we are tackling this exact dilemma head-on. We're going to dive into a truly groundbreaking academic paper that introduces a totally new AI architecture, one that's specifically designed to break through this accuracy versus interpretability trade-off. We're going to see exactly how researchers are finally unlocking the AI black box, and we'll be looking at it through the lens of the fascinating, incredibly high-stakes world of catastrophe bond pricing. Okay, let's dive into our roadmap. We'll start with a quick look at the catastrophe bond market, lay out the AI black box problem, and introduce our hero, CANS, or the glass box. Then, we'll see how researchers actually enforce financial logic, extract a human-readable formula, and finally, analyze the results. Section 1. The catastrophe bond market. To really put the stakes into perspective here, we are talking about a market that hit a record-breaking $61.3 billion in outstanding capital at the end of 2025. That is a massive 24% growth in just a single year. The sheer volume of money moving through this space is absolutely staggering. And while as extreme weather events become more and more frequent, that number is only going to keep climbing. It's essentially Wall Street's highest stakes casino, where the house is Mother Nature. So what exactly are they? Catastrophe bonds, or CAT bonds for short, are fixed income instruments that transfer insurance risk, we're talking earthquakes, hurricanes, massive floods, directly to capital market investors. The mechanics of this are pretty wild. If a qualifying disaster happens, the investors actually lose some or literally all of their principal to cover those insurance losses. But if no disaster occurs before the bond matures, the investors get their money back plus incredibly high yields. Because it's quite literally a multi-billion-dollar gamble against the weather, having perfectly accurate, hyper-reliable pricing models is absolutely crucial. Which brings us to Section 2, the AI black box problem. Traditionally, pricing these complex bonds requires modeling a compound Poisson loss process using what are known as Monte Carlo simulations. Now, this method is highly accurate for sure, but it is painfully computationally slow. When risk managers need to test out thousands of different scenarios, waiting on these simulations creates a massive bottleneck. Now, you might be thinking, well, just use AI. And honestly, they have. Standard feed-forward neural networks can price these bonds with instantaneous speed. The problem? They act as an opaque black box. They spit out a price, but they offer absolutely no explanation, no math, no underlying reasoning for how they actually arrived at that price. And in the world of high finance, if you can't audit the math, you just can't trust the risk. So how do we fix it? Let's get into Section 3, CANS, the glass box. Now, what's really interesting here is this architectural flip. If you look on the left at a standard neural network, the nodes, those circles labeled H1, H2, H3, they contain a fixed mathematical activation function, which you can see represented by the sigma symbol. And the edges connecting them, they just carry simple scalar weights. But on the right, in the Kolmogorov-Arnold network, or CAN architecture, it's completely different. The nodes simply sum things up. That's it, just a summation symbol. All of the heavy lifting, the really complex, learnable univariate functions represented by phi, are placed directly on the edges connecting those nodes. Zooming in on a single node makes this incredibly clear. That standard network on the left hides a rigid, non-linear activation function like your typical ReLU function inside the node itself. But the KN node on the right, it's literally just a summation symbol. By moving the actual learning process onto the edges, representing them as piecewise polynomials or splines, the entire network suddenly becomes transparent. After training, we can actually look at the edges and see the exact mathematical shape the AI has learned. Section 4. Enforcing financial logic. Okay, let's dive into this because there are three unbreakable rules for pricing a cat bond. One, if catastrophe intensity is higher, meaning disasters are just more likely to happen, the bond is riskier, right? So its price naturally goes down. Two, if initial interest rates go up, the present value of the bond's future payout drops, which also lowers the price. And three, if the actual dollar threshold to trigger a loss is higher, well, the bond is safer, meaning the price goes up. The researchers realized that any viable AI model absolutely had to obey these rules everywhere, without a single exception. To solve this, take a look at the thick red arrows here, tracing paths from the inputs down at the bottom, like catastrophe intensity, lambda, up through the hidden layers all the way to the final prediction node. By mathematically constraining just these specific edge paths during training, basically forcing the functions on these red edges to act in a certain mathematical direction, the researchers guarantee the AI can never, ever violate financial logic. They've essentially hardwired common sense directly into the architecture.
Section 5. Extracting the formula. Now that we have a logical, transparent AI, how do we get a formula out of it? The researchers used a brilliant trick called baseline plus residual learning. Instead of forcing the AI to figure out the incredibly complex pricing from total scratch, they feed it a well-known, relatively simple baseline formula first. Then, the AI is only asked to predict the residual, basically the tiny smooth deviation or the error from that baseline. Because the AI is only trying to learn this very small difference, the mathematical formula it generates internally is vastly simpler and so much more interpretable for human beings.
Here is the actual pipeline for doing this. Algorithm 1 from the paper. First, they train the KN on the data. Second, they literally prune it, deleting any weak or redundant edges to make the whole thing sparse. Third, they refine the underlying math grid. Fourth, and honestly, this is the magic step, they lock the remaining active edges into standard known mathematical symbols, like exponential curves or normal distribution functions. And finally, they fine-tune the coefficients. They essentially strip the AI down piece by piece until only a crisp, readable algebraic formula remains.
Which brings us to our final act, Section 6, Analyzing the Results. Mapping out the prediction errors on 90,000 completely new, unseen bond configurations reveals something truly incredible. On the far right, in green, the standard neural network has a tight error distribution. It's highly accurate, but remember, it's still a black box. In the center, in orange, the pre-symbolic KAN is also very accurate, but check out the blue chart on the left. That is our extracted symbolic KAN formula. It achieves an average relative pricing error of just 0.483%. The distribution is remarkably tight and centered right near zero, proving once and for all that you can have an explicit, readable formula without sacrificing that high-end predictive power.
Now, raw accuracy is great, don't get me wrong, but financial logic is just as important. When we look at the really dense data visualization coming up next, the goal is to look for smooth, logical behavior rather than just staring at raw, absolute accuracy.
And this brilliantly illustrates that point. Across this 3x3 grid, the rows represent our key variables: short rate, threshold, and intensity. The columns are our three models: the extracted symbolic KAN formula on the left, the unconstrained pre-symbolic KAN right in the middle, and the standard neural network on the right. Look closely at that middle column. Notice how the curves, especially in the bottom and middle rows, have these completely unnatural wiggles and local kinks. That's financially implausible. A bond's price shouldn't just randomly jump around as risk gently increases. But look at our extracted formula on the far left. The curves are perfectly smooth. They're reliable. By locking the model to a symbolic formula, we traded just a tiny fraction of accuracy to eliminate those weird wiggles, resulting in a model that behaves with perfect financial common sense. To wrap up our data deep dive, let's look at these 3D surface plots. They map bond price against the trigger threshold and maturity. The top row is a zero coupon bond and the bottom is a standard coupon bond. Across both of them, our extracted symbolic KAN on the far left perfectly models that absolutely crucial S-shaped transition region of pricing. As the threshold gets higher to the right, meaning the catastrophe is harder to trigger, the bond's price smoothly ramps up to its full face value. It's this beautiful visual confirmation that the math we extracted from the AI behaves exactly as real-world economics dictate. So let's bring it all together. We started with a multi-billion-dollar problem, the fundamental trade-off between AI accuracy and transparency. But by leveraging Kolmogorov-Arnold Networks, researchers have proven that we really can have both. We can transform an opaque neural network into a transparent, mathematically sound, and highly accurate formula, which leaves us with one final, pretty provocative thought.
If we can pry open the black box for something as wildly complex as catastrophe bonds, what other AI black boxes in medicine, law, or just our everyday lives can we finally open next? Thank you so much for joining me on this explainer. I really hope you found it as fascinating as I did. Keep questioning, keep learning, and I'll see you next time.